Hey everyone, welcome back to the channel. Recently, I shared a video on why, for really fast operations, sticking to a single threaded event loop like Redis does can be super effective. But today, I'm here to flip that narrative. I'm going to show you why a shard per core approach can actually unlock even more performance on modern multi core systems. Let's quickly recap single threaded event loop architectures, like those in Redis. Single threaded event loop architectures use one thread to manage thousands of connections. They rely on non-blocking I/O with the event loop interleaving network reads and writes among queued operations. In theory, I/O latency is minuscule, just a few microseconds, especially when data is in L1 cache. By I/O latency here, I mean the memory I/O latency. Since network latency is in orders of magnitude slower, it seems like one thread can handle tens of thousands of operations without breaking a sweat, really. One thing to note here is that the single-threaded event loop uses multiplexed sockets. There will be a bunch of sockets, and we'll be using non-blocking reads and writes to read and write to the sockets. Thereby, we are not blocked on reading or writing to a single socket. But here's the twist. Modern CPUs are built with multiple cores. Instead of putting all your eggs in one basket, what if you partition your workload across all available cores? Enter the shard per core approach. In this design, each CPU core is responsible for its own shard of data, own partition of data. This means that workload is naturally split up with no need for locks, no heavy contention, just pure scalable parallelism. For the network layer, we'll still have dedicated I/O threads, let's say 4 of them, that manage incoming socket connections. However, each of these threads spawn multiple coroutines or user level threads for each of the connection. These coroutines perform non-blocking I/O with lightweight context switching using mechanisms like co-await. So the coroutine scheduler will be at the user level, and the context switch will not require actual OS level thread context switches. This lets one thread handle thousands of connections without high overhead of OS level thread switches. Now let's dive deep into the storage layer. In a shard per core model, each core gets its own dedicated thread and a shard. Because each thread handles its own partition of data, there is no need of locks or heavy synchronization for that case. Each shard works independently, and communication between the network coroutines and core thread is achieved through a lock-free multi-producer single consumer key, because any network thread can queue operations or pass message to any of the shards, but we'll only have a single consumer because each core thread or each shard thread has its own queue. The coroutines enqueue tasks and receive a future or a promise that gets resolved when the task completes at the core thread. This decoupling means that even if one shard is busy processing complex operations, the others can continue working at full speed. Plus, by keeping operations local to a core, we naturally improve data locality and minimize expensive cache misses across L1, L2, and L3 caches. So, why should you consider this approach over a single-threaded model? Here are a few key benefits. First thing is scalability, of course. With each additional core, you add processing power without the bottleneck of single event loop. Second is reduced block contention. Since each shard is independent, you avoid complexity and overhead of locks. Third improved thing is data locality. Each core works on its own partition, reducing cache misses and boosting performance. Since each core has its own L1, L2, L3 caches, of course. So, of course, no system is perfect. This model also introduces challenges like managing the load across these shards. If it's not balanced properly, we'll just add overhead and fall back to the single threaded model. There's also coroutine scheduler. If it's not efficient, then we'll end up with bottlenecks at the network layer. We also need to handle asynchronous error propagation, and the code will be really complex to debug. But with careful design and managing all these pitfalls, the performance gains of multi-core systems are significant. So databases like Dragonfly, that's why we chose to stick to the shard per core shared nothing architecture instead of the single-threaded event loop. To wrap it up, while the single-threaded event loop is elegant and works wonders when the operations are blazing fast, but the shard per core approach leverages modern hardware. Basically, it leverages all the multiple cores that you have on your processor. This enables us to split work across cores and achieve high concurrency and scalability. So if you are designing a high performance app, maybe key value store or a IO intensive system, uh, use the multi-core, multi-shard approach. Give it a try and see if it works for you. If you enjoyed this breakdown, give this video a thumbs up and don't forget to subscribe and hit the bell icon for more deep dives into system architecture.